So this one is a very uncontroversial presentation on the fact that the special theory of relativity is simply a house of cards. It's built on Coyote's work, a parlor trick that has been played on us by the human condition. And we've believed in it for more than a century because we've used circular reasoning in the tests of its validity. Okay. Basis of the analysis. There's nothing new in terms of the theory presented here. We use the postulate's own, we use the theory's own postulates and premises to decide what will happen from the experiments we set up. There's no flights of fancy off into new theories, but we do make two changes in experimental design. We replace the omnidirectional light source that's sending light off in all directions by an optical laser, just because that disciplines us to pay attention. If the light isn't going in the direction the laser is specifically pointed, then there must be a reason, such as changes in momentum or something. So that just helps us keep track of the directionality of the light. Gets at the point one that was raised earlier on, what do we mean by the direction of the light? The second thing is that the experimental design makes a distinction between what we can call a physical reference frame versus an inertial reference frame. An inertial reference frame is simply a partially defined state of motion. It isn't even fully defined. It's either moving or it's either not moving or it's moving at a steady rate, undefined, and a steady direction, undefined. Not much definition. And you can't tell whether it has no physical existence, it's just a state of motion. It's forever isolated from every other inertial reference frame because since none of them can change their states of motion, you never can get from one to the other. You can just observe them from isolation of which one the observer is in. And he can't even know his own inertial state of motion, so he can't know anything about the inertial state of motion of anything he's watching other than relative to himself. A very information deficient way of gathering data. The physical reference frame has a physical existence, like a spaceship. You can immediately identify which one you're in. And it can move from any one inertial reference frame to another simply by changing its velocity in the right direction by the right amount. And so you can do the experiment in one reference frame and then move it to another inertial reference frame. And you get information doing that that is not available. It cannot be, as we'll see, you can't get that information from an inertial reference frame. You can only get it from a non-inertial reference frame. So, before we get in there, let's look at what was on the playing field when Einstein showed up. It was on Galileo had created the relativity principle from watching a ball being dropped on the deck of a ship. And no matter how fast the ship was going, the ball always fell directly to the deck. Unless you were on the dock watching the ship go by, and then depending on how fast the ship was going, the ball would have different amounts of curvature falling to the deck. And what he decided is that whether the ball is going on a curvature or whether it's falling to the deck is entirely a function of its motion before you drop the ball relative to its observer. Therefore, it's all relative. And if it's all relative, then when you drop a ball to the floor in any reference frame, and you always get the same result no matter how fast it's going, then the laws of physics that deal with the dropping of a ball on a boat is independent of whatever reference frame you happen to be in. They're all equal. They all have the same value. Okay, so that was created by Galileo. Newton codified the laws of motion, laws of mechanics, and still held to Galileo's interpretation of his observations. Same in all reference frames, an interpretation of the observation that when you drop the ball, it looks like it goes straight to the deck. It's an observation, and you interpret it. But there's different ways to interpret it, but we'll come to that. Then Maxwell came along and said, well, he found out that through his bringing together of electricity and magnetism, he developed the speed of light and found out that electromagnetic waves and light is the same thing. and they always work at a particular speed, and you have to be stationary relative to the point of origin to measure it correctly. And Einstein said, well, that would require a special reference frame. There's no such thing. He threw that out, kept that, and did his theory of first postulate. Of course, part of why he did that was because Michelson and Morley had looked for the propagation, medium of propagation, a physical thing that went through all of space that would make it possible for this to be true, and he didn't find it. But you can know it's true simply because it starts from a point, and the fields push each other at a particular speed depending on how hard they can push. And that's all you have to have for this to be right. You don't have to have a physical medium that Michelson and Morley couldn't find. And I'm not saying that that's the only answer. I'm just saying the fact that they couldn't find it doesn't mean you don't have a reason, a physical reason based on observable behavior of electric and magnetic fields for that to be true. And so it's questionable to throw out something. In fact, one of the things that any scientist will say is if you come up with a really great idea that is unprovable, and that there's no possible experiment you could have to prove it or disprove it, that it's too squishy to become a theory. And yet when Einstein picked his first postulate, he said that this relativity principle will apply to everything, not just light, but even to phenomena not yet discovered. Tell me how that can be proven or disproven by a theory. Einstein came up with something based on his faith that a principle that was applied to physical objects would also apply to light, because the principles ought to be the same for both, as a matter of faith, because he said it'll happen to things that aren't even discovered yet. And so a thing adopted as a matter of faith threw out something that Maxwell did very, very carefully from empirical observations, from experiments by Coulomb and Ampere and all that are still accepted today. I mean, there's two clear violations there that today would not be accepted by somebody coming in with a new theory. I point those out just to say there's questions. There are legitimate questions that are raised here. And now we're going to address those legitimate questions here by just looking at the history. What Einstein did was he accepted the Galileo-Newton relativity principle that applies to everything, and it's a law of physics for all motion of all kinds, and that's basically what his first postulate says. And the second postulate accepts Maxwell's speed of light, but it throws out his special reference frame and says it does it independently of the source or the observer, and that is correct, except the problem is that the observer will have observation error if he's moving relative to the source, and Einstein didn't consider that. He said you will directly measure it. He's right that it will actually move at that speed from that location, even if the observer is in motion. What Einstein doesn't understand, or didn't understand, is that creates observation error, and he won't measure it. He's equating observation with reality. That much is at least clear. So, if those two postulates are correct, where am I going? History before Einstein, that should come together. I'm going in the wrong direction.
There are two buttons in one loop.
There we go. I'm grabbing the wrong button. If those two postulates are correct, then light must respond to momentum, because that's part of the laws of mechanics, which are part of the relativity principle from Newton and Galileo. There can be no such thing as absolute rest or absolute motion, because that's what the first postulate says. You can define motion only relative to its frame of reference, as Galileo said. What you see is a function of what the observer's motion relative to what's being observed. And since experiments in all inertial reference frames will produce the result, and all observations made in all inertial reference frames have equal merit, we call that the premise of equal merit. And because experiments in all reference frames will produce the same result, an observation in any inertial reference frame who measures the speed of light his observation will obtain the correct number. That's a key problem. Because what he's saying is, because what happens is consistent, what you will observe will also be consistent. An observation is not necessarily reality. Okay, but all of these beliefs have to be valid for the theory to be valid. You throw anyone out and you get a different answer out of the theory. So what we're going to do then first is say, okay, what did Galileo learn? And he said, in his relativity principle, pre-Newton, if you have two observers doing the same experiment in two different reference frames, no matter how fast they're moving relative to each other, you will get the same answer. You get the same experimental result. So you've got a cannon here, its bore is pointed at the ceiling vertically, you've got an observer, it has a very carefully measured powder charge, that's how fast it'll drive the ball to the ceiling, and that's the distance to the ceiling. He measures the time and gets that answer. No matter how fast this one is moving relative to that one, if he does the same experience, he'll find that all his observations are identical to what those were. And that's what Galileo, he had a ball being dropped on a boat, but this is the same thing. And from that, Galileo said, oh, okay, then motion is entirely relative, the relativity principle. Now, what happens when this guy turns around and looks at his experiment going on in his reference frame, and he looks at that guy's experiment going on over there, and what you have there is here. Here's the guy in reference frame A, here's the guy in reference frame B, each of them is getting the same experience. A looks over at B, which is moving relative to him at the difference in velocity between their two reference frames. He sees the cannon moving away from him at V sub t, and therefore momentum is bending the trajectory of the ball leaving the cannon so that the ball moves horizontally as it goes to the ceiling to stay with the cannon, the target, and the observer, which produces the same observed result. Okay? And this guy sees the same thing, sort of, but both of them see the one going away from himself. They're mirror images because they're looking in opposite directions, but it's the same thing. Now, the question that gets raised is what causes the difference in momentum that causes the angle, I think I used theta in there, to appear. What causes that? And the answer that the relativity theory has, and the special theory of relativity has, because it adopted that as its law of motion, is that it's caused by the difference between the two reference frames. Is everybody comfortable with that so far? Because that is what they decided, but am I properly describing what we get out of the relativity principle as it's been interpreted and put into theory? Because that becomes important, because the question I'm going to raise is what causes the difference in momentum? What causes the momentum to be different between different inertial reference frames? Well, the relativity principle says that momentum is equal to mass times the difference in velocity between the observer and the observed object. Isn't that a correct mathematical statement of what momentum is according to what we just looked at? But the laws of mechanics on which the motions of the objects were governed come up with a different interpretation if you follow the laws of mechanics, because the laws of mechanics are momentum is mass times the velocity of the object, which says then the change of momentum is the mass times the change in the velocity. This is a different description of what will happen when you have a difference. If you get in a spaceship, instead of having two forever magically separated reference frames that can never come together, and different observers in different reference frames, and all you can do is observe them, you get a different kind of information than if we have the same guy doing the same experiment. This is the experimenter in A getting the same result. This is the experimenter in B getting the same result. They're different in their relative velocity, but they're not two separate experimenters in two separate, never to come together reference frames, because this guy has a spaceship and we've only got one experimenter with one experiment is set up in one spaceship, and after he does the experiment here, he gets the results. He fires up the rocket in a spaceship and he changes its velocity for a period of time by the amount necessary to become stationary with everything in reference frame B. And the laws of mechanics say that this change in velocity will create a change in the cannon's motion, which creates a change in the angle at which the ball leaves the cannon, and that this takes place in reference frame B because the change was caused here, and that the guy that stayed behind can see that change, but the guy who's in that reference frame, this guy who took that move to produce what really happens up here, that is moving at delta V, that is moving at delta V, the ball is moving at delta V, and the observer is moving at delta V, and the reference frame, which is objective measure for where things are, is moving at delta V, and therefore he can't see any of the changes. The relativity principle is based on the belief is if you have someone on the dock who does the experiment and someone in the boat who does the experiment, they'll both get the same answer no matter how fast the boat is going. But all we have is the difference in velocity because we're only looking at things from inertial reference frames. But if we say, yeah, but the only way you can get from A to B is by that. And the only way if you're in B, you can get to A is by reversing that. You suddenly know something about the relationship between these two reference frames that brings in the law of mechanics in a different form than the one that is assumed by Galileo and everybody up through including Newton. It is assumed that this is caused, that what he sees is caused by the difference in their reference frames, but he doesn't see that because it's stationary in his reference frame. And the reality is, if the laws of mechanics are right, this is what happens, and the reason he doesn't see it is because his reference frames and his personal sense of motion from his human senses, human condition, all made the same change, which has made his observation wrong. Yes, he got the same thing. You can change this by any amount of speed you will, and every speed goes to a different reference frame, and every reference frame, as a matter of reality, if the laws of mechanics are correct, will have a different angle. But because of this circularity between the observer's own state of motion and his ability to identify and quantify and observe motion is affected by that same change, he will have always the same observation for a change that is different to every reference frame you go to if the laws of mechanics are right. And yet the relativity principle is assumed to be based on the laws of mechanics, but it came from observations of balls that follow the laws of mechanics. The problem is, Galileo thought that the fact that you see the same thing in every reference frame meant that the physical motions were the same thing. And the problem is that Wile E. Coyote's been at work. We're human beings. The only thing we can see is motion relative to ourselves. Now, if we have amnesia and aren't aware that we felt something in our gut that nobody else in the universe felt, that changed how we observe motion, then we could say, oh, well, those are both real. They aren't. If that's real, if that's really where the ball goes, and the momentum changes, the ball has to go there in B if the laws of mechanics are right, and we can explain quite readily why he can't see it. He can't see it because, oops, get the right button. An observer's state of motion determines the coordinate system's state of inertial motion and also his human senses of motion, which determines where you think things are located. From the observed events happen at different points in time. which determines the distance and direction between observed events, which determines your definition and perception of the speed and direction of objects in motion, which all you go around there, you've got a different definition and sense of motion caused by your own state of motion. So when you move from one state of inertial motion to another, you change your definition and perception of what motion is in a manner that makes you blind to all of the changes that occurred that masked your own change, which includes the effect of momentum on the ball. Perception is not reality. So, we have a recipe then for a parlor trick. The human body experiences the same sensations in all inertial reference frames. But if I get in a rocket ship from one and go to another, you know I'm in a different state of motion, but after I get off the rocket ship, I think I'm in the same state of motion. I'm not, but I think I am, because that's all our human body is built to experience. Human condition. Our senses can detect only motion relative to ourselves, and when we move from one reference frame to another, we take our human senses and our coordinate system along with us. And so we'll have a different definition of what motion is, which is totally subjective and different for the observer in every inertial reference frame. So how can you take something like that and treat it with equal merit? Yeah, and inertial reference frame is constitutionally blind to changes in motion because those happen in a non-inertial reference frame. All it can detect is differences in motion, and if you believe that seeing is believing and perception is reality, that means that there can be no such thing as absolute motion, but as soon as you change motion, you made an absolute change. If you pick any reference frame at random and say, I'll use this as base of what actually happens, then you'll find if you take a spaceship to each other different reference frame, the angle of that ball coming out of the cannon will be different in every one if the laws of mechanics are correct, and the observer in that spaceship at those different points will see the same thing. The reason you'll see it is because it changed. I mean, he changed, everything else changed, but he sees no change because he's got that circular definition where his own motion is affecting his ability to perceive. So what we're dealing with here is trying to distinguish between perception and reality. The relativity principle is built on the theory, the implicit assumption that perception is reality. The laws of mechanics, delta P equals m delta V, says ain't so. Which one are you going to believe? If you can accept the relativity principle, you got to throw out the laws of mechanics. And those are still considered good. In fact, they're considered to be part of the supporting information that's in the relativity principle. So what you can believe? So the next point I want to make is that the parlor trick is completely successful. It will truly give you a full set of observations that are absolutely consistent no matter where you take your experiment on your rocket ship. We've shown that you'll misperceive, you've shown that the angle will change, but it won't be perceived. We'll also find that the time duration won't change either. And that is because the change in motion, the steel ball's velocity increases to the vector sum of the cannon charge puts to it plus the change in velocity, which means that you go to a different angle, but you get a different speed. And so if the guy has a really good clock, they'll get the same answer for delta t as he did before. And because his perception of motion changed, it'll look vertical like it did before. And so the parlor trick is fully successful for a steel ball. Its trajectory changed, the speed changes, and everything looks cool. But let's now But it's still a false perception. If the observer cannot see what happens when you get on the spaceship and go somewhere else, then the first postulate is wrong because the relativity principle is wrong. And so your house of cards begins to come down. But what I want to show is you can get all the right answers with a steel ball fired from a cannon, even though your perception is wrong. You'll get at least the same perception. What I want to point out here is with light, you won't even get the same perception. Poor light can't even do the parlor trick. And the reason light can't do the parlor trick is because the speed of light is constant. The cannonball gave the same elapsed time on the longer trajectory because the ball speeds up to the vector sum of its original vertical speed plus whatever delta v is. And so the speed will keep up with the trajectory. Light can't change its speed. So we'll now do the experiment replacing the cannon with a laser and the cannonball with one burst of light from the laser. And we can say that we know where the light ought to go based on the architecture of the laser. You look at the anode going up to a mirror assembly, and it bounces light around in here, and the only light that gets out is what's aligned with that tube. And the physical architecture of the laser says that's the way the light's going to go unless some other force is going to interfere with it, like the effects of momentum. So we can say we know where the laser is pointed, we know where, if absent some other external force or disturbance, that's where the light's going to go. So now that I have a thing I can use like the cannon, a laser, and I'm going to point it up there, this is identical to the cannon experiment. We do the experiment, we get on we fire up our rocket, we go to the next different reference frame, and if light responds to momentum, just like the steel ball would, this has to happen. And that's why everything keeps up with everything else and produces this illusion. So far, so good, right? The problem is right here. We don't get V cannon becomes V is the vector sum of V cannon plus delta V. We still got C. We had C back there. We now have C over here with a longer trajectory. So if this guy has a good clock, it'll look to him like it's vertical, but his clock will tell him, but it's taking longer. That's an observable result. It doesn't even satisfy the same observation, let alone the same actual results. It can't even produce the same observation of time. Now, why has nobody been aware of that? Well, because we take his his observation error, and we divide it by the height of the cabin, and we come up with our own estimate of time. And son of a gun, the only way we can make everything fit our relativity principle is by changing what we think the clock would have read. You know, and the length of the trajectory. We've got to make all of the adjustments of the special theory to reconcile the difference, because we've used this as a light clock, but the light clock slows down as the speed increases, because light has a fixed speed. So light can't even create the parlor trick. But we can ignore that by using the light clock that we are misobserving as our timing piece. So again, it collapses first because the observer, if he moves with the experiment, can't see the changes that do happen, and therefore he does not have equal merit. But in addition to that, light can't even produce the same time interval, and so it can't even produce the same observation, let alone the same real result. When you change from one reference frame to another, rather than just observing them in ground isolation. And when you realize that it's the change in speed that creates the change in momentum, that creates the change in trajectory, not just the difference between the observer and the experiment. So what we're dealing with is that the human condition has caused us to see something different from what the laws of mechanics says must happen, and we have taken what we have seen as being real, and then we build a theory on it. I guess before I go to that one, I'll say at this point, I see lots of disbelief, and it doesn't surprise me because this is not a simple thing to absorb. You have a problem, and that is, do you believe in the laws of mechanics or do you believe in relativity theory? Does delta P equal m delta V? If so, what I've shown you here is correct. If the difference creates it, then this wouldn't be correct, but you also have to get rid of delta P equals m delta V. Either way, you've got a problem. Special theory hasn't ever answered that disconnect between the two. At this point, we can stop because I was going to go to a couple of other things, but I think I'm going to skip anything other than this. Special theory of relativity has two postulates. The relativity principle extends all motion and will always see the same speed of light regardless of the motion of the source or the observer. And that has those 5 beliefs we listed up front, which produce time dilation, space compression, and increasing mass. What I want to show here is that the relativity principle is accepted by everyone as all experiments in inertial reference frames will produce the same result. Not that they will produce the same observation, but that they will produce the same physical result. And we've already seen that those are two different things. But anybody who believes that is true will also believe then that observations in all inertial reference frames must be equally valid. And if that's true and the second postulate is true, you will always observe. It's not that the speed of light actually will be independent of the motion of the observer, but the observation will be the same, regardless of the motion of the observer. And the motion can exist only in relation to the observer's reference frame because all motion is relative. And these are things that the theory is based on, but let's look at empirical methodology. We do experimental design. What kind of reference frames do we use? The only reference frames you see put in the experimental design are inertial. But you can't learn about changes. You can't observe changes in motion from an inertial reference frame. So you've already picked something that's blind to changes. You've accepted something that can only see differences. Why? Well, because in our gut we believe these are true, but you know, the practitioners aren't aware of the fact that this is circular reasoning when you take the theory's own beliefs and design the experiment so it can only see the things that the belief says would be there. Whatever the theory says ain't there, you don't build into your experimental design to look for. That's circular reasoning. You then get conflicting data. Oh, the ball went vertically. No, it went at an angle. Oh, the light went vertically. No, it went at an angle. Well, they're both made from inertial reference frames, therefore they're valid. What we're assuming, as an implicit assumption without stating it, is that, of course they're valid. They're from an inertial reference frame. And that's the only kind of motion that can exist. Therefore, we've got all of the data we need, and it's correct, even though it conflicts. So we're now going to interpret it. We've designed to collect it. We've accepted and validated that it's valid. Now we're going to interpret it. And so some of them disagree with the speed of light, and the only way we can get them to match is by adjusting time, mass, and distance. And so the theory is proved correct. But as long as the design of the experiments and the acceptance and validation of the data and their interpretation are influenced by things that every living scientist knows in his guts are true, they will always be interpreted in a way that proves the theory. And that's what has been sustaining a theory that is internally inconsistent, is because you can only identify the inconsistency by considering what happens in a non-inertial reference frame to get from one inertial reference frame to another, and you find that the laws of mechanics gives you a different answer. when you do it that than when all you have to look at is the difference. So I'll create another analogy, the world is flat analogy. The belief that the world was flat went all the way up almost into modern times. And it was based on people's direct observations of the curvature of the earth, which could not be observed. Every observer had a real empirical observation of whether or not the earth curved. All of them were made in inertial reference frames, and they even all agreed. So according to the special theory or the relativity theory, the world really was flat. It was proven to be flat by numerous experiments, all of which were made in inertial reference frames. Until Magellan, or whoever it was, circumnavigated the world and came back and said, you know, you can get to the same place by going in the same direction for a period of time and end up right where you started, which proves that the world must be round. Now, how did Magellan get that information? Well, not from an inertial reference frame. You can't go around the world without making your ship go fast enough to go around the world. So the only way you can understand inertial motion is by understanding what happens when you move from one inertial reference frame to another. You've got to get information that can only come from a non-inertial reference frame to understand inertial motion. And experimental designs don't look there because of circular reasoning, because the people have been taught to believe in their gut that you don't have to look at in non-inertial. That's a subject for general relativity. But you can't understand inertial motion without looking at how you get from one to the other inertial reference frame. Just as the flat earth people, by observations made in their inertial reference frames, which proved by the principle, but by the logic of the relativity principle, that the earth really was flat, couldn't change their mind until somebody came in with information from a non-inertial reference frame. I'm just saying we're making the same mistake in relativity that the flat earthers made. And I'll stop at that point.
Any questions?
Yes.
Well, I'm go ahead, yes.
I have a city also.
I'll come over here where I hear you.
At first, what is, I have some remarks that what is concerned of Michelson-Morley experiment. Then from 1923, when the galaxy and rotation of our galaxy Milky Way was revealed, discovered the basic supposition of the Michelson-Michelson experiment is wrong, without any doubt, because in Michelson-Morley experiment there are two basic propositions. That the Earth is only one motion in surrounding space in velocity 30 kilometers per second. Do you agree?
Yeah.
Yeah. This is the first.
Big assumptions.
First assumption that Michelson, they didn't knew that motion of Earth in space is also, that could be other motions than the motions around the sun. They didn't knew the rotation of galaxy, they didn't knew that our galaxy is moving to the great attractor. So this assumption is wrong. So without doubt, we knew that the first assumption of the Michelson-Michelson experiment from 1923, we knew it is wrong. Our Earth moves in surrounding space 30 kilometers per second around the sun, 2200 kilometers around the center of galaxy Milky Way rotates, and all galaxy Milky Way as a whole is shifting in velocity 900 kilometers per second to direction of great attractors. So, in fact, all results which could be done from Michelson experiment is wrong at first. Secondly, all experiments which was done by interferometer where the medium were controlled, it means from Fizeau, which was the first experiment with light, and many experiments found out that this interferometer were all placed in a medium, in gas, in water. Fizeau made an experiment with water. And in all of these experiments, the results was expected results. That means they measured the difference in times under the way how this interferometer moves against the lights. The only one experiment was the Michelson model experiment. Also, it is not clear if they measured something or not. Secondly, we knew the Sagnac experiment with the rotating interferometer, which also gives expected results. Yes. So, as we knew that the motion of Earth in space is not that one which expected Michelson and Morley, and we knew that there is another, that in fact the Earth moves in space in compound the velocity and the rotational velocity around the Sun, around the galaxies, to somewhere else, so that we can very high probability suppose that the Michelson-Morley experiment is placed in medium, in rotational, in mutual rotational state. So if you consider some experiment where with a swimmer, in a circular pool, where the water is rotating, and the swimmer is swimming from the center of the pool to the edge of this pool, for instance, in two perpendicular directions, or in whatever direction, the time of his swimming, this distance there and back, will be always the same. So, in fact, we have to say that Michelson experiment came from wrong supposition and expected the wrong results. So that's the first. What I want to say to this. And secondly, for instance, now we live to see in LHC that we have two bunch of protons which are going once against another. They are clashed there, and each one is moving with nearly velocity of light. So it's for me very wonder how I can understand that from the equation for summing of velocity in special relativity,